Good afternoon, colleagues and learners. My lesson today will be on Euclidean geometry. I'm going to treat two theorems in grade 12 syllabus and two theorems in grade 11 syllabus. Right, the first theorem that I want us to look at, it's actually theorem 1 of the grade 12. It reads as follows. I hope you are watching me. The line drawn parallel to one side of a triangle cuts the other two sides so as to divide them in the same proportion. I want us to get this statement correct. I'll repeat. It reads as follows. It says the line drawn parallel to one side of a triangle cuts the other two sides so as to divide them in the same proportion. It is very, very important that when we tackle problems on theorems, if we are given statements, let us interpret, let's get the correct information from the statement. Let's get what the theorem is all about and what is the theorem requesting us to do. When we look at the first part of this, the first part talks about the line which is parallel to one side. It already tells us that in that triangle, there's going to be a line which is going to be parallel to the other side of a triangle. Now, if we look at this triangle, if you look at triangle ABC, it means inside triangle ABC, there has to be the line which is going to be drawn, which in this case it's line DE, which is going to be drawn from side AB and protrude to side AC. And eventually that line, which is now DE, it must be such that it becomes parallel to the other side. It must be parallel to the other side. If you look carefully at this stage, you look at DE having been produced, D being produced at side AB and E being produced at AC, such that when you join them, they make these two to be parallel. Now the statement went on to say a line drawn parallel to one side of a triangle cuts the other two sides, and that is basically what D and E has done to both AB and AC. D has cut AB at this point and E has cut this at this point. So we are told that this line, which now becomes parallel to this, it must divide these sides in the same proportion. What are those proportions? Proportion would be such that when you look at side AD over side DB, side AD over side DB, that must be equals to side AE over side EC. That is what is requested of us. This is what is requested of us. But before we can prove that theorem, I want us to come back to this. Let us quickly look at these two triangles. A triangle ABC and triangle DEF. With a little bit of knowledge, or with the knowledge that we had from grade 10 about having to determine the area of a triangle. The area of a triangle, we normally say the area of triangle is equals to half base multiplied by perpendicular height. Half base multiplied by perpendicular height. This is the formula that we normally use to determine the area of whatever triangle. Fine. Now let us quickly look at triangle ABC and check the side that will be referred to as the base and the height. When you look at triangle ABC, this is going to be our perpendicular height, H, which is written H, or which is denoted H, implying it's the perpendicular height. Why do we say it's perpendicular height? Because this is the height that must always be perpendicular to the base, and such that the angle there is always 90. When we say this is the perpendicular height, we say when you draw such a line, that line must be perpendicular to the base BC, and any line which is perpendicular to two lines which are perpendicular to each other, they must in between them have the angle which is equals to 90. So this is going to be our perpendicular height. Now, if we are going to determine the area of this triangle in terms of the formula, it means it's going to be half BC multiplied by height, which is our perpendicular height. Fine. That was the first triangle that we have gone through. Let's now come to the second triangle, which is triangle DEF. Triangle DEF. And we will also like to talk about the area of such a triangle. We'll also like to talk about the area of such a triangle. Now, if you look at this triangle alone, without having this extension, if you look at this triangle alone, it was otherwise going to be difficult for us to determine the perpendicular height for such. That's why we ended up having an extension. Remember, when we do this, we want to draw the line which will be eventually perpendicular, such that the angle in this case is also 90. So the perpendicular height of this triangle is outside the triangle, but when you look at the perpendicular height of this triangle, is within the triangle. So these are the two types of triangles that I would like us to look at before we can carry on with our theorem, because basically this is what the theorem entails. That is what the theorem that we are going to deal with it entails. Now, let us quickly look at what is requested of us, RTP, which is required to prove. The required to prove expect of us to have this, to say we're looking at line, because we agree that this line divide these two sides into proportion. Therefore, we can come up with a rule in Yakhur. Then it means we are expected to prove that side AD over side DB. Remember, before the extension D, we only had like side AB, but because of this, we now have side AD over DB. This is, now we say side AB over DB over side AE over EC, or side AB over DB must be equals to, or must be in proportion with side AE over side EC. That is what is requested of us. Fine. Now we're looking at this triangle. That is the very same triangle that we had from our textbook. Remember, I've said that for us to prove that, we must always bring this into perspective, because we will not be able to prove that theorem if we are unable to identify in the mother triangle that looks like this, triangles which are going to appear in this form, because now we are going to have our extensions. Remember, what is some learners can say, but what is the reason for extension? The reason for extension is that we have just been given an ambiguous triangle, that from it we don't have the perpendicular heights. Now we must come up with extensions or constructions such that we have perpendicular heights, because basically the theorem, it's all about areas. Now, for you to be able to prove a theorem that entails theorems, you must, for starters, be able to say, let me have constructions in this which will actually give me perpendicular height of certain triangles that I will not mention, but as we proceed, you'll be able to see that. Now, my construction, it says, or under proof, it says, triangle ADE. Where is triangle ADE? Triangle ADE is this one, the upper triangle ADE. Draw height H, which must be relative what? To relative base AD. For now, when we started, we never knew that this is going to be the the base. But since we are going now to have an extension such that we create the height, the perpendicular height, when you draw a straight line that comes from point E up to up to this, which is going to be perpendicular to line AD. That line will eventually be the perpendicular height for what triangle? ADE. Fine. Now let's try to have it. If I'm going to have that, it means this is what I'm going to draw. Remember, in an examination, these constructions will not be made for you. You've got to have them. Fine. Now, this line, it's now perpendicular to AD. Why do we say that? Because this angle is equals to 90. Because the angle is equals to 90. So, this side, I'll refer to it as what? As H. It's my perpendicular height. For what triangle? Triangle ADE. I hope we can all see that. I hope we can all see that. Fine. Now, I am also going to have another height for another triangle. This time, if I'm going to use AE as the base, it means I must have another height for the same triangle. It is still for the same triangle, ADE. This, now it's another construction that I've done. This line which I've drawn here must be such that it becomes perpendicular to line AE. It becomes perpendicular to line AE. So such a line will also be a height, which this time I will be referring to it as what? As K, just to differentiate between the two. This one, it's a height, which I will refer to it as small k, when this one, it's another height, which I'll also refer to it as small h. This is when AE is the base, and this is when AD is the base. When AD is the base, the height is h. When AE is the base, then the height is k. That is the first construction. I mean, if we go through, then they say, join BE. Join BE. I must also join BE and DC. I'm now joining BE. I hope we can all see. I've joined BE, and I've also joined DC. What is the purpose for joining this? Because I wanted to create other triangles. The reason for having this construction BE, having to join BE and DC, was to create triangles BDE. BDE. I'm now having this triangle, and I'm now having triangle CED. Remember, at the beginning this is what we only had. We only had this. But now, due to constructions, we now have additional triangles. We now have additional triangles. The triangle that I've now constructed as my proof was a triangle. It's triangle BDE. BDE. This is where we are, and triangle CED. Fine. Now I want us to prove that indeed, remember, the essence of this theorem is for us, let me write it down, required to prove that AD, side AD over side DB is are equal and in proportion to side AE over side EC. That is what is requested of us. I mean, with all the constructions that we have created, we have together created, then it means we can run with our proof. We can run with our proof. Right. I want us to do this. Remember, because the story is about the areas, let me also bring back these two triangles. Triangle ABC and triangle DEF. I mean, when you prove that theorem, the theorem in question, you must be able to spot triangles, the triangle that looks like this, that is the triangle that will have the height inside it, and the triangle that will have the height outside it. this is the kind of scenario that we are going to come across as we prove that. Fine. Now let me go to my first proof. With my first proof, I want us to look at area of triangle ADE. I don't want us to go the book way, guys. Let's quickly define what area of triangle ADE is all about. Area of triangle ADE. I hope, let me do this, sorry. I hope you are watching the triangle in question. We are looking at triangle ADE. That is the top triangle. Fine. We can deal with this. Why? Because inside this there are perpendicular heights. But I want our point of departure should be such that let's use H. Let's use H. That is, if we are going to use H as the perpendicular height, then it means the base must be AD. What is the definition? The question is, what is the definition of area of triangle? Remember, this is what we've got from grade 9, 10, and 11. We've got this. We are talking about the area of a triangle. So the definition stays the same. It does not change. We don't change anything that we have learned from grade 9, 10, and 11 about the definition of area of a triangle. Fine. However, this is how we are going to do it. We say area of a triangle ADE over area of triangle BDE. BDE. Area of triangle ADE over area of a triangle BDE. Then it means you must come up with definitions of these triangles. It means you must come up with definitions of these triangles. Remember, let me also take you back and say we are going to look at these types of triangles. This is what is going to appear to us. Fine. Let's talk about triangle area of triangle ADE. ADE, let me come here again. I don't think I need to rush because I've realized through marking that most learners are losing marks when it comes to this. And this is so simple. As long as you can make sense out of it and try to understand it. Fine. Half, we say, for area of triangle ADE, we are going to have half. Half of what? Base. What is the base? Our base this time is AD. Half of AD as the base for that triangle ADE. Multiply by perpendicular height. What is the perpendicular height to that? Is H. Fine. When you look at this triangle, guys, when you look at this triangle, this is that triangle. That is that triangle. Fine. Now, however, let's go to triangle. Let's go to triangle BDE. This is BDE. When you look at that triangle, please, we are looking at this type of a triangle. Because when you look at this, there is no way in which you can have the perpendicular height inside this. It means the perpendicular height of that triangle will be outside that triangle. And what will be the perpendicular height will still be this H. Fine. Now, what is the base for that? The base for that will be, what will be the base for that? The base for that will be BD. The base for that will be BD. So it means you are also multiplying by half BD multiplied by what? By perpendicular height, H. Now when it comes to this, you can easily see that the half will cancel the half and the H will cancel the H. So it means the area of triangle ADE over area of triangle BDE will be equals to AD over BD. And that is what the book says. That is what the book says. Let's quickly check on that. This is what the book says. AD over BD. Fine. That was the first pair of triangles that we have identified. Remember, the triangles in question were ADE and BDE. These were the two triangles. Fine. Let's move over to another set of triangles. Yeah, the question that comes, it's asking that why should point E connect DC and DE. It's all about creation of triangles. It's all about creation of triangles. There's nothing more, because when you look at this point E, the point must be such that when we do our construction, we are able to have a triangle CED. That is the main purpose of having this point, which must now join DE and DC together, such that we have a triangle ECD, or yes, CED. So that is the purpose behind it. Thank you for that question. Thank you for that question. Fine. Let me move over now to the next set of triangles. I am looking now at triangle ADE. I wish we can spot that triangle. Area, that's the very same triangle. Remember, the reason why we're having ADE in our first part of the proof is that when you look at ADE, it has two perpendicular heights inside it. So it means we can use this side as a base and we can use that side as a base. But this time, when you look at that, the height in question will be K, not H. So we're still looking at the same triangle, triangle ADE over, we are no more using this one now. We are using the triangle that one learner has just asked about, of saying, why should we have E to join DE and DC? The purpose was to create triangle CED. So we are looking now at area of triangle ADE and area over area of triangle CED. Fine. Remember, we are also talking about the definition of a triangle here. We are also talking about the definition of a triangle. This time when you look at ADE, ADE must be such that now we are going to use this side, AE, as the perpendicular height. No, as the base. We are going to use this side as the base, not that side. We have used that side. Let us now use this side. So it means the definition of area of triangle ADE would be half. Half what? AE, because AE is the perpendicular height, multiplied by what? By K. No, AE is the base, sorry. A is the base. The perpendicular height this time is denoted as K. Over what? Over area of triangle, CED. CED. This is now the triangle in question. Now when you quickly look at this question, this type of a triangle, it is the triangle that looks like this, colleagues, learners. It is the triangle that looks like this. That its perpendicular height cannot be determined within the triangle itself. You'll have to take it outside that. So if we look at that, this is the same with what is the CED? We cannot have the perpendicular height here. Rather, the perpendicular height will be outside. The perpendicular height will be outside. And it will also be referred to as what? Will be referred to as K in this case. Fine. Now, it means the base for this triangle will be EC. Will be EC. So we're saying half. Half of what? Of EC multiplied by K. Remember, the height is now outside. Fine. Now, the half will cancel the half and the K will cancel the K, such that, and this will now imply that area of triangle ADC over area of triangle CED is actually equals to AE over EC. That is what we have come up with. That is what we have come up with. Now, from this, one can come up with this deduction of having to say, then it means area of what triangle? ADE. Triangle AD. Triangle ADE over triangle area of triangle BDE is equals to area of triangle ADE over what? Over area of triangle CED. What is the reason? Remember, we were requested, since, why do we come up with this conclusion? The reason why we come up with this conclusion is because we have made an agreement that this notation is equals to what? Is equals to side AD over side BD. That is what we have come up with. Yeah. This is exactly what I'm talking about. Fine. Then, what about area of triangle ADE over area of triangle CED? This is equals to that. Now, it means the two, it means now we can come up with, say, okay, it means side AD over side BD will have to be equals to side AE over side EC. What is the reason for that? Because both of them are equal. Therefore, this is our concluding statement to say, indeed, what was requested of us is what we have managed to come up with. Let me repeat this. Let me repeat it because I know some of you learners can somehow get lost. Remember, when you're dealing with this, theorem, the theorem is all about you having to have triangles within the initial triangle that we had. This is what we had initially. We had this. But now, seeing that we are able to prove this using triangles or area of a triangle formula, it means you needed to have those extensions. Fine. And it works quite easy. Now, this is what we ultimately have come up with. This is the first conclusion. Remember, we were required to prove this. This is the first conclusion. Then the second conclusion is this one. Now, after having the first conclusion and the second conclusion, we can now agree that since we are dealing with area of triangle, I mean, the formula for area of a triangle, whatever triangle, will still be the same. It will still be half base multiplied by perpendicular height. Now, eventually, because this is what we have concluded here, and this is what we have concluded here, we can just come up with this concluding statement and say, because of that, it means side AD over side BD must be in proportion with side AE over side EC. That is the concluding statement of that theorem. I quickly want us to take one or two examples based on this that I would request you to do them with me. I will not do them for you. I want you to practice doing this. The example in question reads as follows. It says, maybe I must quickly write it down. It says, in triangle ABC, you have line side DE, which is now parallel to side BC. Side DE, which is parallel to side BC. And in this case, we're having side AB, which is equals to 28 millimeters. And the ratio of AE to EC is such that is 4:3. if I've got to explain this, they say the length of AE is going to be 4 units when the length of EC is going to be 4 units. I wish we get that one right. Now they say determine the length, determine the length of side BD. When you look at this statement, it tells you, okay, this if you are given this type of a statement, it will always be accompanied by a diagram. In this case, this is how my diagram would look like. Diagram of triangle ABC. The diagram of triangle ABC. This is how it's going to look like. Say you are having triangle ABC. Fine. But when you look at this triangle ABC, you are going to have the line DE which must be parallel to BC. This is what will always be given to you. This is what will always be given to you. Because at least here we are not solving a theorem. We are actually on a rider. This is what is called a rider. We are applying a theorem. So it means we are having DE which must be parallel to BC as given to the statement. Now, when you look at this, they say AB. Where is AB? AB, this is where AB is. AB must be 28 millimeters long. And when you look at AE, they say AE must be 4 units. This must be 4 units, which I will prefer to write them as 4K. EC will be 3 units. This will be 3K. Such that when you look at the whole side AC, it must give you 7. This must be of 7 units long. That is from here to here. Now they say you must determine what? They request you to determine the side. I mean, this is just a direct application of the theorem. Remember, with the theorem, this is what we have come up with. We have come up with side AD over side BD. Side AD over side BD is equals to side AE over side EC. Side AB over BD is equals to side AE over EC. That is what we have proved. Now we must use that knowledge to determine this. This is what we now requested to prove, the length BD. I'm going to give you 5 minutes, learners, to go through this, and it's only 2 marks question. Let's quickly do that. Take 5 minutes. Thank you, learners. The question that I gave you, can we just go through it? Remember, it reads as follows. In triangle ABC, this is the bigger triangle. We're having DE, which is parallel to BC. This is that. And side AB is 28 millimeters long. AE is 4 units long, when EC is 3 units long. But be that as it may, it means when you want side AC, you are going to combine the two. I mean, 3 plus 4 must give you 7. I don't think we can have a problem with that. Now, the question that I asked was to determine the length of this BD. Fine. And this is what I've done. I've looked at side AB. All right. I've looked at, what is it that I'm looking for? I'm looking for side BD. So I've said side BD over what? Over side AB. What is the length of side AB? Is 28. This must be equals to what? Side EC. But what is the length of side EC? The length of side EC is must be 3K over the length of side AC, which is going to be what? Which is going to be 7K. Fine. What is it that I want? I'm looking for this. So it means I must turn the side BD into the subject of the formula, wherein I will say I'll get rid of this. And how do I get rid of this? I'm multiplying throughout by 28 over 1. So it means this is going to leave me with what? I'm going to have BD being equals to 3K over 7K multiplied by 28 millimeters. Remember, the K can cancel the K. Using your calculator will enable you to have side BD to exactly be equals to 12 millimeters long. So that is what was expected of you. Remember, this is what we are looking for. So you must, every time when you represent this, make the unknown to be the subject of the formula, and that is basically what I do. I mean, that is basic mathematics. I don't think we can get it wrong there. But unfortunately, this was just a 1 mark question. It was just a 1 mark question. I don't know as to whether can I give you another question which may look quite interesting, and I'll give you 10 minutes to answer this question. Thereafter, I'll be moving to the next theorem, which is Pythagoras theorem. The question I'm going to leave you with before we can even introduce that, it reads as it says: D and E are the points on side AB, and let me quickly draw that so that you can see what is it that I'm talking about, so that you can have an idea of what I'm talking about. I'm having triangle here, which is triangle ABC. Triangle ABC. But now, on this triangle, D and E are points on side AB. It means I must have D here. I don't think I also need to do this. What I can do, I can just draw this, because you are not going to be requested to do any construction. Everything has been dealt with at this point. Yours is just to draw what the information presents to you. So this is what we are now having at this point in time. This is point P. We're having E here, and we're having K here, such that DK, line DK, is parallel to line AE, such that this is parallel to that. Fine. Now, the story as it unfolds, it says AD is 2 units, when DB is 3 units. 2K, 3K. So it means AB will be 5K. AB will be 5K. Fine. Another information is that you are looking at line line BE. Where is BE? This is where BE is. You are told that BE is 4 over 3 of EC, such that we can say our BE, if we let BE to be 4P, then it means EC will be equals to 3P. Fine. What is the question? The question is, we must find the ratio CP. CP is to PD. Remember, this is where D is. CP over PD. Obviously, this is the side of a triangle. It's a side of a triangle, which must be related to another triangle that we are going to look at. But the information that we ought to use here is the information which is provided on us. I'm going to give you at least 10 minutes to solve this. When we come back, we will quickly look at it and thereafter look at the Pythagoras theorem. So we are going to have 10 minutes break answering this question. Let's attempt it. Welcome back, learners. Let's quickly look at our question. This is how the question looked like before we went to break, but it's still the same question. It did not change a bit. We had this triangle. It was triangle ABC for starters. But there's this information which was given to us. The information is as it appears. D and E are points. D and E are points on side AB and BC. BC, E will be here when D is there. Right, such that AD by DB, the ratio there is 2:3. It means this is 2 units, 2K units, and this is 3K units. And BE, where is BE? BE is here. BE is 4/3. BE is 4/3 of EC. It means EC is 3 units when BE is 4 units. Now they say if DK, this DK is parallel to AE, and AE and CD intersect at P. This is their point of intersection. If they intersect at that point, find the ratio CP is to PD. Remember, this is where D is. Now, the question is, when you are confronted with this type of a question, you first identify this side. That is, where does this side, what part of, what triangle does these sides belong to? When you look at this, it says CP over, or is to, the ratio CP is to PD. So it means what is this? The triangle in question should actually be triangle CBK. It should be this triangle. So whatever you are going to do, must show the proportionality between for this side and that side. That's why when we start saying, if we look at CP over PD, that must be equals to what? The side which is in proportion to that. It means it should be, when you look, we have taken this side CP over PD. So it means you must also take CE over EK. Remember, we don't have the magnitude of EK or KE. We don't have this. We don't have. Much as we don't. Or this one we have. So it means our unknowns would be the magnitude of this side, that side, and that side. And this is how I've written it. I've said CP over PD. will be in proportion to 3p. Why 3p? Because 3p now is represented by represents side EC, which must be equals to, or which must be over EK, which we also don't know. Now that we have two unknowns here, it becomes extremely difficult for us to at least determine what EK will be, because indeed we don't have the magnitude for this and for that. We only have the magnitude of one side. However, let us go on and say, let's go to EK in another triangle. Remember, EK now belongs to how many triangles? It belongs to triangle CBK and can also belong to triangle ABE. These are the two triangles at which EK belongs to. So if we could not source out the information about EK from this triangle, we can always expand and say, let's try to check what will happen if we can source out information of EK from another triangle, and that triangle in question would be triangle ABE. I mean, let's have a look at that. It means we can source out an information from this about EK, because we could not get it. We could not get EK when we used this triangle. We have quite a number of unknowns. Remember, the purpose of this is to determine this ratio. But since that we now have many unknowns, we can always go to the second triangle to say, let's have a look what's happening in triangle ABE. In triangle ABE, if we say, how do we define EK? EK over the longest side, which is BE. EK over the longest side, which is BE. But the magnitude, do we have the magnitude of BE? Yes. The magnitude of BE is 4p. EK, which is the same side that we are looking for in this triangle. It belongs to both triangles, so it becomes quite easy if we look it from the other triangle. So we are saying EK, the very same side, EK over BE or BE or EB, sorry, over BE, but fortunately we have the magnitude of BE as what? As 4p. So that's why we are going to address EB as not as EB but as 4p, because that is what has already been given to us. This must be equals to what? This must be equals to, we are now in this triangle. It must be equals to side AB, side AD, remember we have D here, AD over what? Remember, we have taken the shortest side over the longest side. So we must also take the shorter side over the longest side. So it means it's going to be, if we take EK over EB, it must be AD over what? Over AB. I'll repeat, AD over AB, because we have said EK over EB. So it has to be, that must be equals to AD over AB. That is what we should represent that. But we fortunately know the value of AD. AD is 2K. AD is 2K. That's why we are going to represent this in terms of 2K over AB. AB will be 5K. Remember, it's just an addition of 2 plus 3, which must give you 5K. Now, at least when we are here, we can able to move, because this will enable us to determine the EK that we could not solve with the first. Here we could not get it. But now that we have moved to this triangle, we have moved away from this because we could not get enough information. We have now come into this triangle. Now it means we can solve for EK. That's why we say EK over 4p must be equals to 2K over 5K. Then turning EK the subject of the formula makes EK to be equals to 8p over 5. That is the value of what? Of EK. That is the value of EK that we have now determined having used this. I mean, this is a simple mathematics that we can just carry on having to turn the EK into the subject of the formula, and such that eventually the K cancels the K. It leaves you with 5. 2 multiplied by 4 is 8p. 8p divided by 5 is 8p divided by 5. 8p divided by 5. That is going to be the value of EK. Fine. But we know we still have that. We still have that hanging. We still have that hanging. Wherein we have said, when we started, we have said CP over PD must be equals to 3p over EK. And now that we have determined the value of EK, we can come and say, we know we substitute the EK with this value. The EK now is going to be substituted with this value. Where EK appears in the first equation, it will be substituted, and that is the simplest substitution that I've made, because I know that EK can be defined by 8p over 5. Right. Now, in mathematics, you know that when we divide, we must take up this value, we take it up, it's going to change. Now it's going to read as 5 over 8, where the p will cancel the 8. 3 multiplied by 5, this must give us 15. 15 over what? 15 over 8. And what is this? This is CP over PD. CP over PD. Remember, the question was for us to determine the ratio CP PD. So it means the ratio CP PD is 15 is to 8. So that is what we have solved together. Fine. I think we are finding this quite interesting. I think we are finding it quite interesting. Now I've got to move to a next theorem, which is a Pythagoras theorem. It is not a Pythagoras theorem, it is theorem 4, which takes us to Pythagoras theorem. I mean, we have been dealing with the theorem of Pythagoras way before in grade 8, grade 9. There was the story in grade 8 about Pythagoras. There was the story in grade 9. There was the story in grade 10, grade 11. And finally, when we go out, we still come across this gentleman with his famous theorem. But now, the theorem that we are going to talk about, the Pythagoras theorem, is actually deduced from this theorem that we are looking at. The theorem reads as follows. The theorem reads as follows. Let me quickly do this so that we can have a clear understanding of what I'm talking about. Let's forget the top part there. This is the theorem in question. This is the theorem in question. It says the perpendicular line drawn from the vertex of the right angle of right-angled triangle to the hypotenuse divides the triangle into 2 triangles that are similar to each other and are similar to the triangle. In essence, what we are given here is this. We are given a right-angled triangle. Let me put away this so that we can have our nice right-angled triangle. The story is about a right-angled triangle. The story is about a right-angled triangle. Fine. Why do we say this is a right-angled triangle? Because this angle must always be equal to 90. If we are having triangle A, B, C, right-angled triangle, right-angled triangle A, B, C. The reason why we refer to that as right-angled triangle because one of its angles is 90. And what is interesting about this is that the side which is perpendicular to this must always be the longest side, which becomes the hypotenuse. The side which is opposite to this is side BC. Side BC is opposite to 90-degree angle. And this is the longest side, which is called the hypotenuse. Now, if we read the theorem, the theorem reads as follows. It says, the line drawn from the vertex of the right angle, from the corner, the vertex is the corner, from the corner of the right angle. So it means what is requested of us is to draw the line coming from the corner of the right angle, the vertex of the right angle. And this line must actually be perpendicular. It must be perpendicular to the hypotenuse. Remember, this is the hypotenuse. And every time when you say the line becomes perpendicular, when we say two lines become perpendicular, it means the magnitude of this must be the same. It means we're having right angles at that. Fine. So we are drawing the line. We are actually drawing the line. I'm trying to hide this so that we can have an understanding of what is going on. We are drawing the line. They say the line drawn, perpendicular drawn from the vertex. It means this line must be perpendicular, drawn from the vertex of the right angle, from the corner of the right angle. The vertex is the corner of the right angle, of a right angle triangle to the hypotenuse. This line must always be perpendicular to the hypotenuse BC. This line must divide the triangle into two triangles. We now have triangle, if I can have this as point D, it means we are having two triangles, ABD and triangle ADC. It divides triangle into two triangles that are similar to each other and similar to the original triangle. All in all, it means we are having three triangles here. We are having triangle, the bigger triangle, which is ABC, ABD, and ADC. We are having three triangles there. Right. The information given to us. All right. What is it that we are supposed to... we are already given the magnitude of these angles. Fine. What is it that we are requested to prove? We are requested to prove that triangle ABC is similar to triangle DBA, and that is also similar to triangle DAC. That is what is requested of us. Fine. Having said that, it means I can divide angle D, which is equals to 180, into D1 and D2. Let me do that. I'm having my D1 and my D2. Fine. What I'm requested to do, learners, is to prove that triangle A, the bigger triangle, is similar to DBA, that is this triangle, and similar to DAC. That is the three triangles are similar. Fine. Now I must source out the information given to me. I must source out the information given to me. The information given to me was such that when this line was drawn, AD was drawn, line AD has divided A into A1 and A2, much as it has done that with what? With D, having divided D into D1 and D2. Fine. Now, if we want to talk about the information which is given to us, I think this is what we should have started. The given information to us is such that, much as we don't know the exact value of A1 and A2, what we know is that when you add A1 with A2, the magnitude of the angle there must be equals to 90, because we were given that A is 90. It's a right angle. Fine. And the other information that we can source out from this is when we add A1, which is this angle with that angle, they must give you 90. That is, it means the sum of A1 and A2 must also be equals to, that must also be equals to D2, because D2 is equals to 90. Because D2 is equals to 90. That is the information which is already provided to us. Now, let us carry on and try to solve this as a theorem. Let us carry on and try to solve this as a theorem. I want us to write a proof now. I want us to write a proof because I wouldn't like to read the information for you. I would like us to go through this so that we understand it clearly, other than when I've got to read it for you. Right. I'm having two triangles that are two triangles which are in question here. I'm having my two triangles which are in question, which are triangles. Let me check what's going on here. I'm having two triangles in question here, which are triangle. My first proof will be based on triangle ABC, and triangle DBA. Let's quickly go back to our triangle. Let's quickly go back to our triangle. I'm saying what we are requested to prove. Our proof will lie. It's of triangle ABC. That's the biggest triangle, because remember I've said we have two triangles, ABC and triangle DBA. The bigger triangle and this triangle. Let's check what is it that we are provided with in those two triangles that we can use to prove the similarity of the two triangles. Fine. In the bigger triangle ABC, maybe I should not remove this so that we are always looking at it. Where are my papers now? Right. I would prefer to use this one. If you look at the bigger triangle, that is ABC. It is triangle ABC with triangle DBA. If we look at that, what is it that we can source out? The first thing that we realize that we can talk about is, for the bigger triangle ABC, we are looking at angle A. Angle A. Angle A in the bigger triangle. Angle A in the bigger triangle, that is this angle. This angle, angle A in the bigger triangle, will be equals to D1 of DBA. Remember, in the bigger triangle, when we started, we have said this angle is 90. Right. But we have also spotted that our D1 is also 90. So it means the bigger, the angle A, that is A1 plus A2, remember this is what we have written, A1 plus A2 is 90. So the whole of A is 90. So it means in the bigger triangles, we have already spotted that this angle D1 will be equals to angle A. So that is what we can write it down. A1, no, not A1, we say A is equals to D1. What is the reason? Both of them are equals to 90, and the reason there is it's given, it's already given. Remember when we had that extension, when we had that construction, it made this angle to be equals to 90. That's the first thing that we can come up with from the two triangles which are in question, triangle ABC and triangle DBA. A is for triangle ABC. I wish I need to repeat this. Triangle A is for triangle ABC when angle D1 is for DBA. Both of them are equals to 90. The reason there is given. Fine. Let's look at angle B. In both triangles, we have angle B. When you look at angle triangle ABC, this is angle B for triangle ABC. And when you look at the triangle DBA, we also have angle B. So we can always say DB, angle B triangle ABC, angle B of triangle ABC is equals to angle B of what triangle? Of triangle DBA. The reason for that is this is common. This is common. This is a common angle in both triangles. So we can write it down. It's common in both. I mean, we have triangle angle B in the bigger triangle ABC and angle B in BDA. So it means B is common. Fine. Let me not do this. Sorry. Fine. Then let's have a look at angle C. What is it that we can talk about angle C for triangle ABC? Angle C must be equals to what? Must be in this triangle. Angle C is for triangle what? ABC. Must be equals to what? Must be equals to A1 of DBA. A1 of DBA. That is, this angle must be equals to that. Maybe people may not understand what is the reason behind. I mean, if we let's quickly do this. If this angle is 90 and this one is 90, fine. For triangle ABC, this angle is 90. This angle is 90. But now, if we look at A1 will not be 90. It will be 90 minus A2, which I can always write it as 90 minus 2, which I can always write it as what? Write it as what? As X. Fine. And also this one, if we check on this one D2 will also be equals to A2 will also be equals to 90 minus A1 will also be equals to 90 minus A1. Fine. Now remember, we say sum of angles of a triangle must give us 180. If this one is 90, then it goes without saying that this one must be 90 minus X. That is, if we, in case you are going to use the X as values there, that is what we tend to have. We tend to have. So now, if we quickly look at this, because I want you to be convinced that this angle is indeed equals to that. Because this one will be, in terms of X, will be 90 minus X, and that one will also be 90 minus X, and that one will also be 90 minus X. So, in principle, what I'm trying to say, if I'm comparing triangles ABC with triangle BDA, when I look at this angle must be equals to that. I hope we have captured that. But in terms of this, we are looking at C for this angle, which is equals to A1 for that angle. So the reason for that is sum of angles of a triangle. Remember, we say sum of angles of a triangle must always give you 180. Sum of angles, if we can just work on that one, it will give you 180. Fine. Sum of angles of triangle. Sum of angles of a triangle. That is the reason behind. That was the proof which was between triangle ABC and triangle DBA. Now, let us go on and take the bigger triangle again. What is this again? Triangle ABC with what triangle this time? With triangle DAC. With triangle DAC. Where is triangle DAC? This is DAC. Now this is the part. We are now looking at this part of a triangle. We are now looking at this part of the triangle. It's the bigger triangle with this part of a triangle. We want to check the information, compare the information, do with the information, because that information will eventually enable us to can prove that the triangles are similar. Remember, this is what we need to do. Fine. So I've gone as far as this and that. Okay, maybe in closing I should closing this one, I should have said, therefore, triangle ABC is similar to triangle DBA. Why? Because we have established that in the two triangles, angles are equal. So it means that the two triangles are similar. This is the first similarity that we come across. That the two angles, the three angles from two triangles are equal, and because of that we can come up with this conclusion. This is the first part of the conclusion that we come up with. Now let us go to the second proof, wherein now we are going to look at triangle ABC and triangle DAC. That is this triangle DAC with a bigger triangle ABC. What is it that we can source out as an information to use? The first thing that I can spot in this triangle is that angle A, that is for the bigger triangle A of ABC, is going to be equals to what? Is going to be equals to triangle D2, angle D2. It's going to be equals to D2. The reason is both of them are equals to 90. And fortunately we are given that. Their magnitude is 90. And that is what is given to us. Fine. That is the first pair of angles that we have identified to be equal in the two triangles, triangle ABC and triangle DAC. That is, this angle is equals to the bigger angle. Fine. The second part of that, just like we did with B. Remember, with the first part we have said B was common in both. B was an angle for ABC and was an angle for DBA. So it means we can say the same with C. C is an angle for ABC, and C is also an angle for DAC. So it means C is common in both triangles. C is equals to C, and it is common. It's a common angle in both of them, in both triangles. Fine. And last but not least, let us go back and check at B versus A2. B versus A2. I mean, if we write this as 90 minus X, for what? For triangle ABC, this B will be equals to A2, because we have said B, this B, if we write it in terms of 90 minus X, will also be equals to, in another triangle DAC, will be equals to A2, which is also equals to 90 minus X. So if we are going to write that, we are going to say B is equals to A. The reason for that, it's simple, is that these sum of angles of a triangle. Now, in essence, good people, we have proven that three pairs or three angles from each triangles mentioned here are equal. So it is because of that that we can conclude by saying it means triangle ABC is also similar to triangle DAC. Fine. Then the underlying, remember, we were supposed to prove this. So it means if triangle ABC is similar to triangle DBA, and triangle ABC is also similar to triangle DAC, it means the three triangles are actually similar. That is the conclusion. Triangle ABC is now similar to triangle DBA, and that is also similar to triangle DAC. DAC. Fine. This is what the theorem entails. That is what the theorem entails. Fine. Now I want us to move, and I want us to quickly move, because this theorem it actually introduces us to Pythagoras theorem. This is just an introduction to Pythagoras theorem. Remember, you dealt with Pythagoras every time when you came across a right-angled triangle. So Pythagoras theorem, it's a theorem that entails a right-angled triangle. Now, the conclusion that we have come up with here actually introduces us to this lovely theorem of us, Pythagoras theorem. Now, learners can ask, why do you say this? I want us to go back to our first conclusion. The first conclusion of first two triangles, which read as triangle ABC being similar to triangle DBA. From that, we can come up with this to say, if I look at, if I've got to look at side AB, let's look at side AB, over side DB. When triangles are similar, it means their sides are in proportion. So I'm looking at proportional sides here. Side AB must be proportional to side AB. Hence I write AB over DB must be equals to side AC of this triangle. It is the smallest side of this triangle, which is AB, over the smallest side of this side triangle DB, divided by the longest side AC over is it AC? AC, I think I'm getting it wrong here. I'm getting it wrong. No, it's not supposed to be AC. It's AB over DB. This over that. That is correct. And this should have been BC, yes. This side over BA, which I can always write it as what? Which I can always write it as BA or AB. Now, if I need to cross multiply here, it means I'm going to have AB squared, which is going to be equals to BC multiply, that is this side multiplied by that side, BC multiplied by DB. That is the definition of AB squared. Fine. And this is the information that I've sourced out from where? From this similarity. I'm taking proportional sides now. Let me repeat that because I know some learners can confuse this. We are looking at AB. When you take this side, AB must be over this side. AB over DB must be equals to this side BC over BA, which in this case I've just rearranged it as AB. I mean AB and BA are one and the same, such that when I cross multiply it gives me AB squared, which is going to be equals to BC plus BC multiplied by BD. Fine. Now let's also quickly look at this and say what happens in triangle if you still have triangle ABC. I mean, these are conclusions. This is the conclusion for the first part, and I'm now going to the conclusion for the second part. That is this conclusion. triangle ABC is similar to triangle DAC. Now in here, I'm going to have this. I am saying AB again. AB, that is this side, over it has to be over that side. It has to be over DA. Over DA, because these are in proportion. AB over are in this must be equals to BC over what? Over what? It has to be BC over, I've taken this one, let's go again. We have taken AB over AD, BA over AB, that is correct. Then I must take BC over AC, BC over AC. Do you have anything here? We don't have. We don't have because I also wanted to relate AC. Maybe if I can say this is also equals to, if I take now this side, the outside side, the longest side, AC, if I can take AC over DC, I also take this, the longest side, as DC. Now, remember I've already proved AB, so I can always leave this one behind and concentrate on this one, because now this is going to give me what? My AC squared. When I multiply this with, it's going to this is going to give me AC squared, which is going to be equals to what? Which is going to be equals to this one is going to be equals to what? It's going to be equals to CD, which is CD or DC, CD multiplied by CB. I mean this multiplied by that. So I have proved that AC squared is equals to CD multiplied by CB when AB squared is equals to BC multiplied by DB squared. I mean this one I've taken it from here. Maybe others could have said, but you could have taken this one BC over AC, and you could have taken that is let's start again, BC over AC, which is this one, and having forgotten about this one, BC over AC, which was supposed to be equals to AC over DC. That is still correct, because that enables us to come up with this conclusion. That I don't have a problem with that. That is still correct. Fine. Now let me take the last one, because I want to have all these sides. I want to have all these sides with me. Now the last one, the last conclusion will be such that a triangle DBA is also similar to triangle DAC. Now from that we can do this. We say, let's look at side DB. Because if these two triangles that I've mentioned are similar, they are similar to each other because both of them are similar to the bigger triangle. Remember ABC. Both of them are similar to this triangle. This is the conclusion that we have come up with. Now I'm here. I'm looking at this. Fine. We are saying if that is the case, then it means we can come up with this conclusion to say DB over what from that triangle? It must be over DA or AD. This must be equals to BA over what from that triangle? AC. DC. But since we cannot come up with the conclusion again here, we can extrapolate and take it further to say, but we know that we can have side DA, side DA over side DC, now taking the outside, over DC, also being equals to that. Also being equals to that. Now it means, since I cannot come up with a conclusion for this, I can stick by these two relations, wherein now I'm going to have DB, side DB over DA, being equals to, because they are in proportion, being equals to DA over DC. So that now it allows me to have my cross multiplication wherein now I'm going to have DA or AD squared, which is now going to be equals to DC multiplied by DC multiplied by BD. Now these are the conclusions that I've had, guys. Now let's quickly recap, because I've said this is just an introduction of Pythagoras theorem, and say from Pythagoras theorem we know Pythagoras theorem says the hypotenuse. If we go back to our triangle, this is the hypotenuse, BC squared. This is what Pythagoras theorem proclaims. BC squared must be equals to what? Must be equals to AB squared plus AC squared. The longest side, the square of the longest side, must be equals to the sum of the square of the other two sides, AB squared and AC squared. That is what Pythagoras theorem entails. But now, for us to be able to do that, we can say we have proved the following. We have proved that AB squared is equals to BC plus BD squared. That is what we have proved. AB squared being equals to BC multiplied by DB, and AC squared being equals to CD multiplied by CB. However, when we come to this, we realize that we want BC. We want BC, and we want BC. Now we can express AB in terms of BC multiplied by CD, and AC in terms of CD multiplied by what? Multiplied by CD multiplied by CB. From this is our AB. What is my AB? AB is BC multiplied by DB. This must be squared, remember, because AB squared plus AC. From this we have said AC is CD multiplied by CB. This must also be squared. Remember, that is what we are now looking at. Fine. Now, I want us to come here and say it means we can have this. It means we can have the following. We can have AB squared plus AC squared being equals to what? Being equals to remember, we want BC squared. We are saying BC is what? BC is equals to AB squared plus that. Now, maybe I can relate. Let me relate to this as B. Remember AB squared. My AB squared was BC multiplied by multiplied by, I think I was wrong. I was wrong. I was not supposed to do this. Sorry. BC multiplied by DB plus AC squared is CD multiplied by CB. Now, from this side, I mean, I can always relate to this as BC. CB can always be BC. From this, I can take out a common factor, which is going to be BC. Therefore, it means I'm going to have, if I have my BC as a common factor, it means going to leave me with what? 1 multiplied by DB plus 1 multiplied by CD. That is the conclusion that I can draw. Fine. Now, but we must not forget that we are saying this is equals to what? This is equals to AB squared plus AC squared. Fine. Let us quickly look what is DB and CB from our triangle. From our triangle, what is DB? DB is this, and what is CD? CD is this. CD plus BD give us BC. So it means, in essence, these are the smallest sides which make us BC side BC. Because for you to have BC, you must add BD to DC or to CD. So it means you're having BC multiplied by BC. BC multiplied by BC is what is BC squared, which is actually a theorem of Pythagoras. So by so doing, it means we have proved Pythagoras theorem. But for you to have proved that, you should have taken it from where I took it from. Otherwise, you could have not understood the similarities and these other things and the deductions that we have come up with from this lesson. I wish you had a wonderful lesson on Euclidean geometry, and I wish you carry on with this exercise. There is one thing interesting about mathematics. For you to understand this part, you need to practice it. Please let us not do it the book work. Let us try to make sense on the information that has been provided to us since from grade 8, grade 9, because I believe we have dealt with geometry from grade 8 up to grade 11. So now here we are just applying the knowledge that we have gathered in those lower grades. I wish you have a wonderful afternoon and good luck in your mid-year examination. Surely this will be there. And I thank you.